on the last lecture, we considered the following example. Let me just remind you. So I will go way faster today because we already had this. So I'm considering basis in R2 and basis in R3. So pay attention that I took just some pretty arbitrary basis, right? So of course, I could use the natural basis in R2 and R3, but I just wanted to consider just some relatively arbitrary basis. And we considered the map from R2 to R3. So, okay. And I just said that I will determine this map by the following. So action of this map is determined by the following action on the basis vector. So essentially, I'm applying my map to the basis vector, and I know that this is what I will get. Pay attention, I haven't specified the map yet, right? I'm just saying that I will define this map through this information, and this information, this and this one, so action on this vector of the second vector of the basis. So I'm just saying that it's enough to completely specify the linear map. So if I know that the map is linear, so okay, so I can also write that this is equal to, so I want to represent this map through the vectors of my basis in R3, this one. So it will be, so how to represent a vector with respect to the specific basis, you're supposed to know already. So we studied this. So essentially, I can just remind you that you just write some system of linear equations and solve it and find the coefficients. So essentially, idea is that you just saying that, okay, this is equal to C1 on 1, 0, 0, vectors of the basis. 0, negative 2, 0, plus C3 on the third vector of the basis. And this is equal to this vector. So as a result, you can write it as system of linear equations and solve it for C1, C2, C3. So here it's already done. And here correspondingly, this vector can be represented also with respect to the corresponding basis. So it will be 1, 1, 1, 0, 0, 1, 0, negative 2, 0, plus 0, 1, 0, 1. Okay. So as a result, looking at this, I can write that representation with respect to the basis D of H applied to to 0. So this representation is nothing else but 0, negative 1/2, 1, right? Just coordinates vector. And correspondingly, representation with respect to the basis D of H applied to the vector 1/4 second vector of the basis is nothing else but 1, -1, 0. Okay, so then now I just wanted to show, and I have done this before, that if you consider any vector v, which can be represented as C1 on the first basis vector in the original vector space plus C2 on the second basis vector, so immediately you can compute this linear transformation applied to the this arbitrary vector, because using linearity property, you know that this will be nothing else but that. And because this and these are given already, right? So you can just substitute this here and this here. And as a result, you will know that this will be nothing else but, okay, I will write it like that, 0 C1 plus 1 C2 multiplied on the first basis vector plus negative 1 C1 minus 1 C2 multiplied on 0, -2, 0, second basis vector plus 1 C1 plus 0 C2 multiplied on 1, 0, 1, third basis vector of the basis D. As a result, you know that if representation with respect to the basis in the original vector space, basis B, of the vector V was C1, C2, in other words, these are coordinates, the vector of coordinates with respect to the basis B, then you know that representation with respect to the basis D of H of V will be nothing else but this 0 C1 plus 1 C2 -1/2 C1 minus 1 C2, this, and the last is that, right? 1 C1 plus 0 C2. Okay, or you can do the following. You can write this as multiplication of the matrix. Just use, we will use the following notation, and I will remind you where it comes from, where I introduced this originally. So it's BE. So this is representation with respect to B, and you're getting exactly 0 C1 plus 1 C2, -1/2 C1 minus 1 C2, 1 C1 plus 0 C2. Okay, so we previously, so essentially, you see, we got, and this is representation with respect to the basis D. So essentially, you see, we start from the coordinate representation with respect to the basis B, multiply by this matrix, and getting coordinate representation of the result with respect to the basis D. So let me remind you now. So we considered, so how we introduced this matrices, column vectors, and everything. So we introduced first, we were considering arbitrary system of linear equations Can you confirm that you can hear me? Yeah, thank you.
Yeah.
Because you see, when I was editing the video of the previous lecture, so I didn't dropped out. So just something happened with the connection to Zoom. So I figured out that in the end, when I told you about the quiz, so my audio just cut out. So, I mean, I'm sorry about that, but this is beyond my control. So this is why don't be surprised if I will be asking you, so whether you can hear me or not, okay? So you see, we introduced coefficients matrix. So, and also we introduced the column vector of unknowns. And also we introduced column vector of the right hand side. So pay attention, how many equations we have? Could you repeat, please?
We have n equations.
M, okay. And how many unknowns do we have?
Unknowns.
N. So, okay, here, how many rows this matrix has?
M.
How many columns this matrix has?
M.
Okay, how many rows this vector has?
M.
And this vector?
M.
Okay, great. So now, let me consider multiplication of this matrix. Let me introduce multiplication of this matrix on this vector as, so I just want to have it in this form. What does it mean that one vector is equal to another?
All the components are the same.
Yes, exactly. All the components, two column vectors are equal to each other when all the components are the same, right? So now I want to just from the point of view of notation for simplicity, I want to have this A multiplied on the vector X equals to the vector B. So B is the vector of right-hand sides. This is the vector of unknowns. This is coefficients matrix A. So, okay, because these two vectors are equal to each other, so B1 has to be equal, to this expression, right? So essentially how I multiply, how I'm getting the first component of multiplication of the matrix on the vector. So AX, the first component, is nothing else. So I require it to be nothing else but that. In other words, I take this first row of the matrix and multiply it on the whole vector, corresponding components, right? So A1 multiplied on X1, then A12 multiplied on X2, A13 multiplied on X3, and so on till AY1N multiplied on Xn. So essentially, and then I add them. I'm getting this. So I can write that AX, the first component, is equal to sum J goes from 1 to N, A1J, XJ. In other words, so first J is equal to 1, right? Plus J is equal to 2, plus J is equal to 3, plus and so on, and the last term is J is equal to N, right? Okay, could you tell me what will be, could you tell me the formula for ith component?
It should be summation from J equals 1 to N of A sub ij x sub j.
Yep, exactly. And this will be AI1X1 Is it clear or not? So essentially, we introduced originally before the multiplication of matrix on the vector just to have this convenient notation. AX equals to B. That's it. So it's just nothing else but compact notation. So we introduced this coefficients matrix A, right? We introduced column vector of unknowns, column vector of the right-hand side. So it was just convenient to introduce, to say that, okay, let us say, just for this convenient notation, that this is how we multiply matrix on the vector, right? That's it. Okay, now, could you tell me, so first of all, how can I write the column vector? So if this, so this matrix is M by N. So pay attention, this is an agreement. If you will have a look at this notation here, you see, first index is the row index, second index is the column index, right? Column number. So for example, element A23, 2 means it's the second row, 3 means the third column, right? Any questions? So you see, one of the reasons why I ask you if there are any questions, I want to be sure that you can still hear me. So please, at least somebody say something like, it's clear.
It's clear.
Okay, thank you. So we have M by N matrix, because you see, agreement is that the first is row and then it's column, right? So M by N means M rows and columns. So could you tell me, so when because before we were not doing this often, right? So I just mentioned that, and that's it. So now, how can we specify the vector of unknowns, the vector, column vector with n entries?
N by 1.
Right. So we can say that this is nothing else but n by 1 vector, right? What about these? So could you, what is the dimension of the vector of the right-hand side? So you see we have m entries. Yes, m by 1. So when we multiply, you can see that the column index of the matrix is going away, right? But the vector has to have exactly the same number of entries as the matrix number of columns, right? Otherwise, this multiplication is not defined because we don't know what to do. If we have more columns than entries of the vector, then we don't know what to do with the remaining columns. Or if we have less columns, we don't know what to do with the remaining entries of the vector. So the result, have a look. In order for the matrix vector multiplication to be compatible, you need to have here, it has to be the same, right? And then when you multiply matrix on the vector, so this internal index is used and it goes away. So you see, you had m by 1, n by 1, n went away. So what is left is m by 1. Is it clear or not? You can also understand it like that. You see, you had m columns, m as in Michael, m rows, sorry, of the matrix. So as a result, here you will get also m rows. Why? Because you will be taking every row and multiplying on the vector. So every row vector multiplication will give you entry of your resulting vector. Okay? So this is exactly what we are doing here. Pay attention. We are taking this column, this row, multiplying it on this vector, and getting exactly this, right? Then taking the second row, multiplying on the vector, getting exactly this, right? Taking the third row, multiplying on the vector, getting exactly this. Is it clear or not?
Yes, it makes sense.
Thank you. So, by the way, so if you remember what were representations of your corresponding maps of the basis vectors, representations with respect to corresponding bases, right? So have a look here. 0, -1, 1. 0, -1, -1/2, 1. Here, 1, -1, 0. 1, -1, 0. Is it clear or not? So if you want to find matrix representation of the homomorphism with respect to corresponding bases B and D, you need to find to what vectors your homomorphism will map vectors of the original basis B, and then represent the resulting vectors with respect to the basis D, right? Okay, now let me write it in a more formal way. Definition. Suppose that V and W are vector spaces of dimensions n and m correspondingly, with bases B and D, and that H is the homomorphism from V to W. Homomorphism. If the representation with respect to D of H, okay, you know, I need probably write it like that. Beta 1, beta 2, beta n. Vectors of the basis B. H of beta 1. So corresponding representation is H1, 1, H2, 1, HM1, and a representation with respect to the basis D of H beta 2 is H12, H22, HM2, and representation with respect to the basis D of H beta n, sorry, is H1n, H2n, HNN. So have a look. This index is the same as this index, right? So I'm saying that it's the first coordinate of the representation with respect to the basis D of the homomorphism of the first vector, right? Second coordinate of representation of the first vector, mth coordinate of the representation of the first vector, first coordinate of representation with respect to the basis D of the homomorphism of the second vector, second coordinate of the representation of the second vector, mth coordinate, and so on. So first coordinate for representation with respect to the basis D of nth vector, second coordinate, nth coordinate, m coordinate. So you see it's m. Okay. So if we know these representations, then the representation with respect to the bases B and D of the homomorphism matrix representation. So pay attention here. I'm just saying that this is matrix representation. I just introduce it as the definition. H11, H21, HF1, H12, H22, HF2, HM, oh, sorry, H1M, 1N, H2M, HMN. So B, D. So this is the matrix representation of H with respect to P and D. So pay attention. Right now, I'm just saying that this is a matrix representation. Okay. So now let us consider the following map. Example. So let me consider map from R3 to the vector space of linear polynomials, which is the following. Okay, if one would work with the natural basis, okay, let us work with natural basis really. So then I can say that representation with respect to the, okay, let me call this N1, the following basis 1x, right? So representation with respect to N1 of to A1 plus A2 Could you please tell me what will be this representation with respect to these natural bases for the space of polynomials of degree 1?
Would it be 2A1 plus A2, then negative A3?
Yes, thank you. So it's this. Okay, now let me suppose that I'm working with a natural basis in R3. So which is this. Right? So then representation with respect to the natural basis 3 of the corresponding A1, A2, A3 obviously is nothing else but exactly A1, A2, A3, right? So this is how essentially this is how we introduce the column vector, right? So vectors in vector space of column vectors. This is why we call this basis natural. By the way, if I will exchange the order, will representation change or not?
Yes, it will. The
Yes.
A3 and A2 would switch.
Yes, these two will switch, right? Okay, thank you. So, but for now, let me not do this. Let me just use the natural basis. Okay, now, could you please tell me, okay, could you tell me how to, so what will be the map of these? So what will be the result? Could you tell me?
2.
Right. So let me write everything in details. 2a1. So this is my a1, right? Plus a2, which is 0, minus a3, which is 0. So it's not exactly 2, it's 2, 0, right? Vector. Just based on that. Right or not? Or
Yes.
if you like, we can do it like that. So let us apply these, right? So have a look. We defined our homomorphism through this formula, right? So then we substitute 2 multiplied by a1, which is 1, plus 0 multiplied by 1 plus negative a3, which is 0, multiplied by x, which is 2, right? Okay, now, second vector of the basis. Could you tell me what will be the result?
One, 0.
Yes, because it's 2, 0 plus 1, negative 0, right? So it's 1, 0. Or if you use this definition, so it's nothing else. I mean, correspond to. It's not equality, right? So it's 2, 0 plus 1, 1 plus negative 0 x, which is equal to just 1. Okay, and let us find the action on the last vector of the basis. Okay, could you tell me what it will be equal to?
0, -1.
All right. Negative a3. a3 is equal to 1. So it's 0, -1, which corresponds to 2, 0 plus 0, 1 plus negative 1 x, right? So which is negative x essentially. Okay, so we know how our homomorphism acts on the natural basis, right? So then what is interesting that if I consider arbitrary vector v, which will be, let's say, v1 plus then if I want to apply my homomorphism to the vector v, I need to do essentially the following. I need to, using linearity, use this, right? Right? And if we need to represent it, we want to represent the result with respect to basis n1. So we need to do the following, that the representation with respect to n1 of the homomorphism of v will be nothing else but correspondingly v1 representation with respect to N1 of the H V2 plus representation with respect to N1 here. With respect to N1 H, which can be written as, so the matrix which consists of these column vectors or I can write it as, just a second. Here is, and multiply it on V1, V2, V3, just like that. So, which can be written as, have a look, 2, 0, 2, 0, first column, second column, 1, 0, and third column, 0, negative 1. Multiplied by V1, V2, V3. So what we are getting? We are getting that 2, 0, 1, 0, 0, negative 1. It's okay. N3, N1 representation. So this is V1, V2, V3 representation with respect to the basis N3 equals to correspondingly 2 V1 plus V2 minus V3, and this is representation with respect to the basis and N1, sorry. So is it clear what I've just done or not?
How did you include N1?
Because you see, this, for example, is nothing else but representation with respect to N1 of the homomorphism of 1, 0, 0, right? Clear or not?
So N1 is 1 in X?
Yes, it was written before. Have a look here. N1 because here we have P1, and here we have R3, so this is why I called corresponding basis N3. Is it clear or not?
Okay, so it was a process from N1 to N3.
From N3 to N1, because we start from N three-dimensional basis right here, and we end up in N1.
Does that always mean that final matrix that we wrote will be the domain first and then the codomain?
Yes, because have a look here. So when we introduce the matrix, right, we start from V which has a basis B, right? And the resultant W, which has a basis D, right? So so we are going from B to D, right? Have a look here. Because have a look, we multiply later. So what we are doing, we are taking the domain, right? Representation with respect to some basis of the vector from the domain, multiply by the matrix, right? Or matrix representation of the homomorphism, and end up in the codomain, right? So the result, B domain, result codomain. But this is just notation, right? So idea is that here, have a look, all these representations, all of them are with respect to the basis D in codomain, right? Pay attention, D, D, D. Is it clear or not?
Yes, thank you.
This is very important because this is what you will be doing in the session afterwards. So now let me formalize what I've just done. Let me just write it formally. I will formulate it as a theorem. Assume that V and W are vector spaces of dimensions n and m with basis B and D, and that H mapping V onto W is a linear map. If H is represented by the representation of H with respect to the bases B and D as H11, H21, M1, H12, H22, HM2, H1N, H2N, HMN, so BD representation, and V belonging to the vector space V capital, domain of the homomorphism, is represented by representation with respect to the basis B of V is C1, C2, Cn. Then the representation of the image of V. Or you could say result of application of our homomorphism to V is representation with respect to the basis D of homomorphism of V is the following. And this is with respect to the basis D. So this will be part of your homework, just to go again through, okay, proof. So this is formalization of previous examples. Also, it will be part of the homework, just to do this on a more formal level. And also, let me give now matrix vector product, formal definition of the matrix vector product. The matrix vector product of M by N matrix and N by 1 vector is given by A1, 1, A2. So pay attention, M by N, N by 1, internal index has to be compatible, so it will be used during multiplication, and we get M by 1. So pay attention. First, I introduced matrix vector multiplication, just like you remember how I introduced matrices. I said that, okay, I don't want to write all the time this A1, 1, X1 plus and so on, because this X1 and pluses were not giving me any new information because I was working only with coefficients. This is why I said that, okay, let me write this so-called matrix of coefficients, which is nothing else but the table of coefficients from the system of linear equations. Okay, I wrote it. Then I said that, okay, let me write this column vector, which is an object which consists of unknowns. And then I also could write the right-hand side as the column vector, which consists of the entries of unknown of the right-hand side. And then if I want to use this compact notation just because of that, then I need to introduce matrix vector multiplication in exactly the form which we considered before, right? Now, have a look. You can see that this appears naturally, this matrix vector product appears naturally if you are talking about, here it is, about representation of the result of the application of the homomorphism, right? And here we have representations of the result of application of the homomorphism to the basis vector of the basis B, represented with respect to the basis D, right? Column by column. Okay, is it clear or not? I will do an example, another example right now. So, but if you have questions, please ask me. Okay. Okay, can anybody confirm that you can still hear me?
Yes.
Yes.
Okay, great, thank you. So let us consider the d by dx homomorphism linear map applied to polynomial of degree, okay, 3 probably is too much. Let's say degree 2. So if we start with a polynomial of degree 2, right? So quadratic function. Then when we differentiate, so we will get polynomial of degree 1, right? So let us consider this. And for now, let me work with the okay. So let me work with a little bit strange basis. So here, basis B, here, basis D. Okay, basis B will be the following. 1 plus x, 1 plus x plus x squared. So D will be x plus 1, x minus 1. Okay. So now have a look. First, let me remind you how if I will start from the polynomial of the form quadratic polynomial of this form, how to express this with respect to the basis B. Okay, so what I need to do, I need to write C1 on 1 plus C2 1 plus x, C3 1 plus x squared, right? And I know that this has to be equal to a0 plus a1x plus a2x squared. If you like, I can write it like that. Okay, so now let me collect together all the terms. I will get C1 plus C2 plus C3 on 1 plus C2 plus C3 on x plus C3 on x squared. And this has to be equal to the same, right? So then equating, I will get this, right? So from here, I can do backward substitution. So I know that C3 is equal to A2. Okay, let us go further. I substitute this instead of C3, and I'm getting that C2 is equal to A1 minus A2, right? And from here, substituting here this and this, I'm getting that C1 equals to A0 minus C2, which is A1 minus A2, minus C3, which is A2. So which would give me, so this minus on this minus will give me plus, which will cancel with this minus. So as a result, I will get A0 minus A1. Okay, so now I know that representation with respect to the basis B of A0 plus A1x plus A2x squared, sorry, is nothing else but A0 minus A1, A1 minus A2, A2. Is it clear how I've done this or not?
It's clear.
Okay, perfect. Now, let me compute, so let me consider the following: B0 plus B1x. So this is polynomial. So if this was a polynomial belonging to P2, this is polynomial belonging to the P1, right? So please, let me represent this polynomial with respect to the basis D. Okay, once again, I have C1 on first vector x plus 1. Not C1, C1 is not good. C1 we already used. So let me use D. D1 x plus 1 plus D2 x minus 1. So, and this has to be equal to B0 plus B1x. Okay, so again, collect together all the terms. We are getting D1 minus D2 multiplied by 1 plus D1 plus D2 multiplied by x equals to B0 multiplied by 1 plus B1 multiplied by x. So we need to equate polynomials are equal to each other when corresponding coefficients are equal. So from here, if I add them, I'm getting 2D1 equals to B0 plus B1, or I can say that D1 equals to 1/2 B0 plus B1, right? If I use the difference, so for example, 2 minus second line minus first line, so I'm getting 2D2 equals to B1 minus B0. So D2 equals to 1/2 B1 minus B naught. Okay, so now I know that representation with respect to the basis D, B naught plus B1x is nothing else but 1/2 so D, and here it was. Okay, now ddx p2 p1. Okay, so d dx applied to a naught plus a1x plus a2x squared. Could you tell me what it will be equal to?
A1 to A2X.
Exactly. So, okay. Representation with respect to the basis B of, oh, no, with respect to the basis D, sorry. Of A1 plus 2A2X, what it will be equal to? Hello?
Be 3/2, and then
Why
minus
3/2?
1/2.
Why 3/2?
Let's see. So you got 1 plus.
So you see,
two.
B naught, right, is this, right? Right? So have a look. It's this, right? B1 is 2A2. Right or not?
Yeah, sorry. I was going too fast, I guess. Sorry.
It's okay. We will do this. Or you can do the following. Let us consider d by dx, c1 multiplied on 1 plus c2 multiplied on 1 plus x plus c3 multiplied on 1 plus x squared. Okay, let us do this. So we will get, so we can first write it in this form. So c1 plus c2 plus c3 multiplied by 1 plus c2 plus c3 multiplied by x plus c3 multiplied by x squared. Could you tell me what will be the result?
C2 plus C3 plus 2C3X.
Exactly. So, okay, what is the representation with respect to the basis D of C2 plus C3 plus 2C3X? This is our B naught, right? And this is our B1, right? Yeah, 1/2. Go ahead, please.
1/2 times the quantity C2 plus C3 plus 2C3. And then 1/2 times the quantity C2 plus C3 minus 2C3.
You see?
Oh, wait, is it minus A1, not minus? Okay, sorry. I just
B1,
forgotten what
yeah.
the representation was.
It's okay. It's okay, okay. So minus C2 minus C3, or you can say like that, right? So which will be, and this is with respect to D, which will be essentially one half C2 plus 3 C3, right? And here it will be 1/2 negative C2 plus C3. Right or not?
Why?
Just computed this and computed that.
Oh, okay. Yeah, sorry, I just missed it.
Okay. Okay, so you see, if I start from C1, C2, C3 with respect to the basis B, my H will give me 1/2 C2 plus 3 C3, 1/2 negative C2 plus C3 with respect to the basis D, right? Or let us, so these, I mean, I can immediately write matrix representation. So essentially, you could just looking at them. Just looking at them. So I can immediately write what it will be. It will be, first of all, C1 do not enters right here. So the result, I know that here I will get zeros because when I will be multiplying, oops, sorry, too many rows. First of all, this is 2 by 1, and this is 3 by 1. So I know that this has to be 2 by 3, right? Matrix. So this, I will have 0 and 0 here. Then 1/2 C2, 1/2 here, negative 1/2 C2. And here 3/2 and 1/2 here. So I can do it like that. Or I can just apply d by dx to, for example, the first vector. So C1, I mean, the first vector of the basis, I will get 0, which can be represented as 0, 0 with respect to the basis d. D by dx of 1 plus x, second vector of the basis B, I will get just 1, which corresponds to the, how can I represent 1? So it has only, where it is, here. It means that B1 equal to 0, B0, okay, 1 is equal to 1 by 1 plus 0 by x. So this is B0, right? So B0 equal to 1, B1 equal to 0. I'm getting 1/2 negative 1/2. And d by dx is equal to 1 plus 2x squared, which can be represented with respect to the basis d. So this is 1 multiplied by 1 plus 2, sorry, not x squared, 2x. 2 multiplied by x. So this is my b naught. This is my b1, right? So I'm using this formula, 1/2 b naught plus b1 and 1/2 b1 minus b naught, the representation. So which will give me 2 plus 1, 3/2, and 2 minus 1, 1/2. Surprisingly, this is exactly that. This is exactly that. And this is exactly that. I would never believe it, but it's true.